First, before starting the last class, I would like to make an announcement to meet you, all of you, next year, because the announcement is of the European School of Differential Geometry that will be held in my university in L'Aquila from June 22 to July 3. So in 2026, and it is a part of a big project, a European project, where there will be a school every other year. So the first one was in Granada last year, and the next one will be 2026 in L'Aquila. And just to give you an idea of, it's already, I mean, everything is a everything is, the project is advanced. So there will be 3, 4, 7 mini courses by, I mean, the title are not written here, but they're already done. So it's Antonio Alarcon, Alessandro Carlotto, Eleonora Dinezza, Frank Fosternik, Antoine Song, Melanie Rupfin, Wolfgang Ziller. And then there will be all those speakers. So students can apply to come. There will be some fellowships, but in fact, the fellowships are for the participating countries, so are just for European countries, unfortunately. For the moment, we have not enough money to invite everyone, but there is a selection anyway to come, and students can come with their own project or something. So please, if you like this kind of subject, and if you, I mean, if you can, you are really invited to come. And this is also for colleagues, because it will be interesting also for colleagues, I believe. So, okay. And the project will go on, and in 2028, it will be in Grenoble, the school. And then later, we think that it will be in England. It's not already completely decided, but it will be in England. Okay, so let us give this last information about maximum principle. If you remember, yesterday we were looking at height estimates. We stated them, and it was oops, and it was like I just stated quickly height estimates. So we have to prove that if you have a domain and if you have a CMC graph, omega to R, so you consider the graph of U as CMC H as a CMC as constant mean curvature H, then U is less than or equal than 1 over H. Okay? Okay, so how to do that? The proof is by Serrin. And in fact, as usual, with the many Serrin theorem, the proof goes far beyond the technique goes far beyond the thing that you want to prove. I mean, you can prove many things with this kind of method. So he considered the Laplace-Beltrami operator on the surface. You can call sigma the graph of U. So you consider the Laplace-Beltrami operator. So you can write the Laplace-Beltrami operator, in fact, in terms of the metric. So I write it because I will need it. So if you take a function h from sigma to R, so the Laplace-Beltrami operator of H is, I am in R3 for the moment. I mean, you can do it in Rn, but I do it in R3. So it's ij from 1 to 2. This is a standard formula, of course, square root of the determinant of the Gij. Gij is the metric on the surface. Gij is the metric, the induced metric by R3, in fact, sigma. And then the derivative with respect to I of the square root of the determinant of Gij. And then Gij, the inverse matrix, inverse, times the derivative with respect to J. Okay, so this is the Laplace-Beltrami operator. Okay, we have to, this is a general fact for any surface. It's not necessarily for graphs, of course. Let me just give you the formula, you can compute the Laplace-Beltrami operator of U and also of another function that will be useful for us. Okay, so one can compute that the Laplacian of U is equal to 2h over, let me write it as WU, where WU is classically 1 plus the gradient, the norm of the gradient square. So this is a computation. And another computation that is a little bit more involved, but it's a computation, is that 1 over the Laplacian of 1 over W is equal to minus 4h squared minus 2k times 1 over WU, where k is the Gaussian curvature. Okay, one can say, but why are you, this is, okay, is the graph, but why are you doing this? This is a very important as a geometric meaning, because it's the third coordinate of the normal vector to the graph, okay? So if you write n, the normal vector is minus, I mean, it's a choice, but W minus U2 WU 1 over WU. Okay, so this is in fact N3. Of course, you can choose the other normal vector, but it is a choice, it's nothing. This will only change the sign of the mean curvature if you change the normal vector. Okay, so Serrin had the idea of considering this function, p equal to minus hu minus n3. And why? Because in fact, if you compute the Laplacian of phi, the Laplace-Beltrami operator of phi, it's a test function. Yeah, you will see. What does it give you to u? So it's minus h times 2h over wu, and then plus 4h squared minus k times 1 over wu. So you do the computation, and you have, am I right? I know I forgot the tool here. I was, so here you have 2 over wu times h squared minus k. And this, you know, that is positive, larger or equal than 0, except the umbilical point is 0. So it's larger or equal than 0. So phi is a supermonic function. So let's say how it is at the boundary. What happens to phi at the boundary? So u is 0 at the boundary. So this first part is 0. So it's negative. Okay? So it's minus u over wu. It is negative, less or equal than 0. Maximum principle, I mean, no, you cannot say it in principle with the maximum principle that we gave, because we gave we have to prove that this Laplace-Beltrami operator satisfies the maximum principle. This is very quick, but assume for the moment that it satisfies the maximum principle. If this satisfies the maximum principle, then phi will be less than or equal than 0 in omega. Okay, so what does it mean? Let's see. So we have minus h, u minus n3 smaller or equal than 0. Now you have to look a little bit to the sign of u and so on. So assume that u is positive somewhere. So if u is positive somewhere, that's for sure. As you choose the upper pointing normal, h is negative. Okay, so h is smaller than 0. So you divide it by minus h, and you have u smaller or equal than n3 divided by minus h. Okay, but this means smaller or equal than 1 minus the norm of h. Clearly, because one of n3 is smaller or equal than 1. Okay, so of course, if u has negative point, you do the same. I mean, you're just to play a little bit with sign, but it's so you have the height estimate. Okay. You have just to prove that this satisfies the maximum principle, but this is really quick. This is why I wrote it like that, because if you develop this expression, you get a linear equation. So you develop a little bit this stuff, you get that this, you can write like G, I write directly the last formula, I mean, what you get by developing, simply. You get the Gij, the inverse matrix, di, dj, h is the function that I am differentiating, plus di of square root of determinant of Gij times Gij inverse over the square root of the determinant of Gij times djh. And so this is a second order linear equation for a differential equation for h. There is no term with h, it's just the derivatives. So the maximum principle. I mean, everyone knows that for the Laplace-Beltrami operator. I mean, not always, because it depends a little bit on the I'm not going into details about that. I mean, you can do height estimate for other kind of graphs, for other kind of space, but for example, it doesn't hold all the time, height estimate. So, because, for example, you can do it, as I told, in a higher dimension, but you can try to do in a hyperbolic space, and there you have to consider certain kind of graphs. Sometimes it holds, sometimes not. It depends on the graph that you choose. And for example, if you take, okay, let's say that height estimate for CMC surfaces does not hold. No, do not hold always. For example, if you take my favorite space, that is H2 cross R, that is the product on the hyperbolic space. So this is the hyperbolic space, the hyperbolic plane. You take the product, it is a manifold. And then, and you can represent it, for example, you take the disk model here. So you have a disk times R, but on the disk you have the hyperbolic metric. So this is H2. This is at infinity, of course. So here, in fact, you can find rotational surface that are CMC H for any H smaller or equal than 1/2. And clearly here you don't have height estimates because they are going to infinity here and they are larger and larger. So if you enlarge your domain, you're not going, the height goes to infinity. So it's not possible to find height estimates here. It's a little bit like, it's not like minimal surfaces, but I mean, it's not, height estimates are not always true. Okay, and of course this depends on the shape of the equation. Okay, so this is the first application, and it was just an application of the linear maximum principle, in fact. Okay, now we are going to prove Alexandrov theorem. So let me see if I want to say something before. Okay, I stated. So Alexandrov theorem. A proof of this, Alexandrov theorem. You can find it in the OPF book. It's a differential geometry in the large. It's a very classical book. And it's famous because it's very easy to remember, is the number 1000 lecture notes in mathematics. Okay. And this is, I think, is the second part. It's a big book, chapter 7. It's very nice to read. So if you have time, you can go to read it. This is for the students. Okay, so Alexandrov theorem, let M be a CMC H different from 0 surface, compact, embedded in R3. Then M is a round sphere. Okay, this is a classification of CMC surface in R3, kind of classification. There is I told you, maybe, I don't remember if I told you the first day, that there is a brother theorem that is OPF theorem that many people know, the brother. We listen about that many times in this conference. But I just mention it because, so it's an OPF theorem. And this, M, CMC H different from 0, surface, topologically a sphere. Words in R3. Immersed. Then M is a round sphere. Why I mentioned that? Because I want to say this is another classification, of a CMC surface. This time you assume that it is already topologically a sphere. But I mentioned that because both are sharp. Because at a certain point, a mathematician, Wente, find out tori CMC immersed in R3. So, yeah, sharp. Okay, good. So, and also Alexander theorem and Dopf theorem were generalized in different ambient manifold in different dimension. There are some places where Alexander theorem is still an open problem. For example, in the Heisenberg space, because I mean, the proof that we are going to give needs a lot of symmetries. Okay, so with that proof, you can prove it only if you have a lot of symmetries. There are other proof of Alexander theorem, but you still need some symmetries. For example, in the solvable group, I'm talking about three manifold just to. In the solvable group, you can prove Alexander theorem once you have proven Hopf theorem. It's Galvez, Mira. No, Daniele and Mira, Benoit Daniele and Pablo Mira that prove that. But still, in solve, you have two family of orthogonal planes whose symmetries, with respect to symmetries, are isometries. So even if the isometry group of Sol is small, but then you have those family and they helps you a lot. So, I mean, in NIL, you don't have it, so it's open. Anyway, let's prove it in R3. So the first thing that we have to, we are going to prove that the surface has a lot of symmetries, but then, so you need the lemma before everything. It's a very simple lemma, geometric lemma, that is very, sometimes, I mean, you can think that it's obvious, but Hopf proved it in a very nice way, in my opinion. So if a compact, no, let me first define what's it, I mean, just if you have a plane P, it's just a notation. You call the direction of P a normal to it. And so the direction is, in fact, a point on S2. Okay, so the direction of P or of the family of parallel plane to P is a point of S2. Okay, so if a compact surface M has a plane of symmetry in all directions, then it is a round sphere. Okay, it's obvious, yeah, but why? I mean, in fact, you need much less. I'm going to prove it. Proof. It is enough if you if the set of the direction contain an interior point. It is enough. Okay, so let's say like that, denote by sigma the subset of S2, that in this case is S2, corresponding to the direction of plane of symmetry, corresponding to the direction of the planes of symmetry. So our assumption is sigma is equal to S2, but in fact, it is enough, and you will see it in the proof, that sigma contains an interior point. Okay, it cannot be a curve. It must contain an interior point. Yeah. Yeah, but no, I don't distinguish. I mean, I can do the, if it is symmetric with respect to one of the two directions, it is symmetric also for the other direction. So I get both. Because I don't know from which side I'm going to, from which side I'm arriving. So I can, I mean, it has...
Does the direction of the normal, it plays a role. So pointing North Pole and South Pole.
Yeah, but I mean, I will...
Different orientation, right?
Yes, but I will choose a direction in the space.
Okay.
Okay, one, fixed. And then I will take the family of plane orthogonal to this direction, and I will find the plane of symmetry.
Yes.
Okay, yes. I can choose also the other way around.
Yes.
And I have already a plane of symmetry.
Yes.
So, I mean, it is also this but nevertheless, it's not very important. I mean, you can also decide that you say you choose only one side, but it's a little bit difficult to choose a side, no? Because you don't know where choosing it. So this is why you are. I mean, at the end, sigma need to be very small. I mean, you don't need the S2, you don't need the half of S2 for the proof. But we will prove that there is, in all directions, there is a plane of symmetry. And if you decide that you only come from, I mean, you can decide that once you prove for this, you are not going to prove also from the other side. Yeah, you can decide it, of course. So it's right, but as we are going to prove only for one, because they are all equal, so it's not, okay. So how it works, you can assume that this interior point is the North Pole, for example. So N, North Pole, is the interior point. So for sure, as it is an interior point, if you take an equator here, and a geodesic, you can take, you can say that all the directions corresponding to these geodesics correspond to plane of symmetry. So pick up one and take the two planes corresponding to this, P1 to this direction, P1 and P2, and assume that here there is an angle alpha. So what's very easy to prove is that if the surface is symmetrical with this, with respect to these two planes, it is invariant by a rotation of 2 alpha around the intersection of these two planes. Okay, so let's say that the angle between N and V, how you write it, the angle, I don't know, the angle between N and V is alpha if M is symmetric with respect to P1 and P2, then it is invariant by rotation, by a rotation of 2 alpha around the axis P1 intersection. You have to convince, but it's a computation, in fact. You can write down the rotation, and it's like that. Okay, so we are almost done, because you can take, of course, this works for all the points on this geodesic. So you have that your surface is invariant by rotation of small angles around, the axis is the same. So it's invariant about a small rotation about this axis, but small rotation produces all rotations. So it is invariant by rotations about the axis. So let me write it. M is invariant for small rotation. Around this axis, let's say. But so for rotation, small rotation generates all the rotation, and then V was arbitrary. So you can choose it on any geodesic exiting from the North Pole, and you find out that M is invariant for all rotation around any axis. So by V is arbitrary. So M is rotationally invariant. Okay. So now, in order to prove Alexandrov theorem, we must prove that M has a plane of symmetry in any direction. Convinced? Not too much. Franz is not very convinced. Why not?
But it's close to N, right?
Yeah, small.
Small.
Small, but once you prove that is small, I mean that is invariant by those small rotation, is invariant by all the grid circle rotation.
Yes. Right.
So then you take all the, I mean, as N is interior, you can take all of them. It's invariant by all of them. This is small rotation generates big rotation. This is why. Sorry? And we fix N is an arbitrary point. I mean, you fix a point. I took the North Pole for simplicity. But in fact, in our case, we can choose any of them because all the points are interior. But it is enough that it is an interior point. And then choosing choosing which it's up to rotation. It's fine. Okay. It's an arbitrary choice. Up.
Here is the only compact surface in which all the geodesics are closed because.
Sorry, it's no, yeah.
Okay, does that lemma follow from the fact that the round sphere is the only compact orientable surface in which all the geodesics are closed, because in torus and for higher genus surfaces,
you don't need it. You don't really need it. I mean, it's or maybe yes. You don't need the uniqueness. I mean, it's not the only. You don't need that it is the only one. You need that you have this configuration, but you don't need that it's the only one. No, the theorem now follows because M contains a sphere. Okay, because it's invariant by rotations. So in our situations, the one connected component is compact, it is the sphere. Okay, so the theorem follows, the lemma follows by that. Yeah.
So sorry, I mean, I think I still have a confusion here. You never get a rotation around the horizontal axis, a direction. You see what I'm saying? You have, these are always very, very close to N, correct?
Yeah.
So your directions are sort of in a little, cap, in a little.
Yeah.
Why is that what you should think? Yeah, then it's clear. Yeah, but the assumption is we just have this small neighbor. That's the assumption. Why do you get everything? You don't get all axes. You never get the horizontal direction. Exactly. Then that's the argument. Then you can generate all of SO3. Right. Right. That's what I mean. You need only that because you can then combine these rotations to make to generate SO3. That's what you get, right?
Yeah, you need to know
you
that.
Need to know very small disks so that it works. Yeah, that's what you.
You need to know that after that small rotation generates all rotation.
Oh yeah, yes. They do. Yes.
Yeah. That you need, of course.
Right.
I agree. Okay.
No, I get it. Yeah.
But it's something. I mean, I had to think about that because it's something that one thing. Yes, but you have to think a little bit about. He still has doubts, but I am going to finish. Then we can talk about that. So now let us prove that M has a plane of symmetry in any direction.
Ma'am, I have a question, if it's okay.
Yeah.
Just to confirm, what does it mean for M to be symmetric with respect to a point?
I wrote M is symmetric with respect to a point, so I was wrong. Doesn't mean anything. Wait a minute. Where I wrote, okay? Okay. So now, as I told, we are going to use what is called Alexander reflection method. Alexandro reflection method, and also people from analysis call it moving plane method. Moving plane method. Okay. To prove that M has a plane of symmetry in any direction. So fix one direction. That means fix a family of parallel planes. So you can parameterize. So let N be a direction. That is a point on S2. And PT, a family, the family of parallel planes orthogonal to M. And you parameterize them, like, for example, if it is N, so you call it P0, this one, and this is the direction of T smaller than 0, and this is the direction of T larger than 0. This is just a choice. But how I choose it, so I have here my surface. Let me do in an intelligent way, if I succeed. I have a surface here. You can have genus, you can have everything. And I choose this first plane far away from my surface. Of course, the surface is embedded, so you have a compact component W such that the boundary of W is N. And you can also assume that your mean curvature vector point inside W, okay? Because the curvature is, I didn't say it, but I assume the curvature is positive. So you take your normal vector inside and your mean curvature vector will point inside. Okay, so as the W is compact, I can choose my first P0 disjoint from W. Okay, now I'm pushing P0 towards my surface, and I will find a first vertical plane that I'm going to call PT0 that has a first contact point with the surface. Of course, it can be more than one, but as they are the first one, here it is tangent. So PT0 is the first plane touching M. So PT0 is tangent to M. Okay, so now you go a little bit farther. You call it PT, and you start to give names to things. So this part will be called MT minus. This part will be MT plus. Let me first define PT plus equal to the union of PS such that S is larger than T0. So this half space, the half space in this direction, in this part, and the PT minus the other part, the union for S smaller than T0 of PS. So here you have PT plus, and here you have PT, sorry, so here PT0, because for each, I'm sorry, here is T. Now for any T, you define, not only for PT0, for any T, you define the two half space. Okay, one on the one side and one on the other side. Okay, so in fact, who is MT? MT minus is M intersection PT minus, and MT plus is M intersection PT plus. Okay, so, okay. Now you do the reflection with respect to this plane. So you call this MT star. So MT star is the reflection of MT minus with respect to PT. So a couple of remarks. When T is very close to T0, MT minus is a graph of bounded slope on this on PT, on a part of PT. Okay, so T close to PT0 to T0, and T is a graph of bounded slope. And also, MT star is contained in W. Okay, at the beginning is like that. Okay, so you go on, you keep on going, and you continue doing reflection, continue doing reflection. Till the first, let's call it tau, such that one of the following happens. The following happens. Okay, one, M tau star is no more contained in W. W is the open set. Is compact component that's bounded. Is open. I'm not considering the boundary. It's easier. So it's no more containing W. The two M star tau is not a graph of bounded slope. Okay, you have to think a little bit to get convinced that one of these two things happen at a certain point. For sure, I mean, when you do reflection, there is a moment where M star will go out of W. Okay, everything is compact, and it can go out in two ways. These are the two ways it can go out. Okay, so let us go a little bit further. So we will see that in each of these cases, there will be a plane of symmetry. So it's very easy now. It's here that you will use the maximum principle. So the picture, okay. Let me do a first picture for the case one. Assume that one happened. Assume that one happened. So I mean, let me see if I'm able to do it. It should be like that. So this is the plane of symmetry. Okay, so this is p tau, this is m tau minus, this is m tau star, this is m tau plus. Okay, so in the first point, when it happens, it's clear that you have at least one point like that is called P. So there exists P belonging to m tau star intersection m tau plus, such that m star tau and m plus tau are tangent. And one on one side of the other, because this is the boundary of W and this is inside W. So, and one on one side, and how to write it, on only one side of the other. And then you also can notice that if this is the tangent plane, the mean curvature vector point on the same side, yeah, because you were here. I mean, I don't know which is the point. You are here in the reflection, so you reflect also the mean curvature vector, so they both point to the same direction. So by the maximum principle, they coincide. So m star tau coincide with m plus tau by the maximum principle. And then you're done, because this means that the right-hand side and the left-hand side are equal. So m is symmetric with respect to tau. So p tau is a plane of symmetry. So just a little picture for the case 2. I write it here. 2. Assume 2 happens. So here the picture is like that. I make the plane here, then I do like that, and something like that should be fine. So this is p tau, and it's not really good, but I mean, it stopped to be. Here you have to think that it is tangent to this. This is the tangent plane, P, P, M. This is P, okay? So this is m tau minus, m tau star, and m tau plus. So if you look at these two surfaces, they are tangent at a boundary point, but they have a common boundary. So here, they also have the same mean curvature vector. So here you use the boundary maximum principle that holds. Okay, I didn't enter in much details about the boundary maximum principle, but it holds as well. So they should coincide. Boundary maximum principle. That implies that m plus tau coincide with m star tau. And that's, so p tau is a plane of symmetry. But the direction was arbitrary, and the first direction that I choose was arbitrary, so you have a plane of symmetry in any direction. Okay, so I think I'm done. I finish here. I'm going to finish here.
Questions?
Hello, ma'am. Just wanted to know the idea in the hyperbolic plane case. Do they also have similar result, right?
I cannot hear you.
Hyperbolic plane case. Hyperbolic plane.
Hyperbolic plane. Okay. Yeah. Okay. In the hyperbolic space.
Is the analogs they use horospheres instead of?
Yeah, you can do exactly the same proof in the hyperbolic space with the totally geodesic planes of the hyperbolic space. And in the sphere, so space forms. So in the spheres you can do, but you see that the first thing we have to do was to find one plane of the family of parallel plane that was disjoint from the surface. So if you take the sphere, in fact, this is not guaranteed in general that you can find it. So it is true, the theorem is true if you take the surface in a half sphere. In this case, you can do it. Okay, so, if you want. But
Thank you.
Any other questions?
Just, Ben.
Thanks for your talks. I had a question about the proof of the Sarin theorem, and maybe you already commented on this and I missed it, if so sorry. But I was wondering if you could talk about a little more about the choice of the test function phi, or like how you choose like that specific phi. I guess like the Laplacian of it's kind of nice. So maybe you get some cancellation or.
Yeah. This is exactly. I mean, the choice that Sarin did was exactly. I mean, was the good. It was the good idea was to take a function that was subharmonic.
Oh, okay.
Yeah. So you needed subharmonic, and you know that h squared minus k is positive. So it was looking to such a function. I mean. I have no geometric intuition behind it, and I don't know many people having geometric intuition behind it. I mean, it's a good test function. It was Sarin that thought about that. Okay. But in fact, if you want, the quantities are very geometric, no? Because it's the height and it's the n3
height component.
Yeah. This is important. I mean. Why it works only for graphs? It's U, of course, but it's also because N3, the normal vector, the third coordinate of the normal vector on a graph, it's constant sign. It's negative or positive if you choose one of the two, I mean, upward or downward, but it doesn't change sign. On any other surface, it can change sign, so it doesn't work. But in fact, as I told you, if you have a surface that is not a graph with a boundary on a plane, you have a height estimate that are 2 over h instead of 1 over h. And that's because you can prove by using Alexandrov reflection method with horizontal planes that the half of the surface is a graph. And this is really Alexandrov reflection method. It's not nothing more than this. So this is why I didn't prove it to you.
Any other questions?
I mean, it's something.
Here you can have one, it goes out, or it doesn't go out.
No, but
when it doesn't go out, somehow you seem to.
But no. But both cases are going out in some sense. You have two ways of going out. Two ways of going out.
Yeah.
One is to touch an interior point with an interior point. The other one is to touch a boundary point with a boundary point. You have to convince you that you cannot touch a boundary point with an interior point, but this is natural because you are doing reflection. The point on the plane that are the boundary point stays fixed. So the reflection. So it's exactly this. I mean, you have two ways of going out.
Argue when you go out, then there's be a first point of. There must be at least some point where you start leaving. So
yes, exactly. And you take the very first
that's
one.
either in the interior or it's in a boundary.
Exactly.
Right. Okay.
Yeah.
If it's on the boundary, then you fail to be a graph.
Yes.
At that point, right? So the slope over that.
The slope
plane
become
over that plane goes
infinity.
Unbounded.
Yeah, unbounded.
Further questions? Again for a full level.